Okay, students, this is the third video in developing the equation of motion. So recall what happened. We had a rod with a spring, a damper. We worked out the deflections of the spring and the rod. We then used these deflections and velocities to work out the corresponding spring force and damping force. For the particular problem, we had a pivot and forces in the upwards direction to the right hand side of the pivot would generate positive torques in an anti-clockwise direction, and forces on the left hand side of the pivot in a downwards direction would then generate positive torques, in other words torques in an anti-clockwise direction. Just be careful, the forces would have different sign notations on either side of the pivot. If we defined a force in an upwards direction towards the right hand side as positive, a positive force times a moment arm would generate an anti-clockwise torque, and that would be positive according to our sign notation for positive torques. If, on the other hand, we defined a force in an upwards direction as positive, then this force in an upwards direction would generate a clockwise torque, which wouldn't make sense if that is positive. So we said our notation, the x is positive on the right hand side, the y is positive on vertical upward direction, and positive angle is positive in an anti-clockwise direction. By implication, this would give you the positive fx in a towards the right. Positive y in the upwards direction would give me a positive force in the y direction, and a positive theta in an anti-clockwise direction would give me a positive torque in an anti-clockwise direction. If the force is positive on the right hand side, this force would generate an anti-clockwise torque that would be positive according to a sign notation. Looking at on the left hand side, a force in a downwards direction would generate counterclockwise torque, which would then be positive. If the force on the left hand side was positive in upwards direction, this would then generate a clockwise torque, which wouldn't be positive. That's why we have to swap the directions of the forces on the right hand side and left hand side in order to consistently generate a force that would generate a corresponding torque with the same correct sign notation. So looking at our diagram, we have the spring force is this expression in terms of a positive theta, and then the damping force is this expression in terms of a positive theta and by implication a positive angular velocity, where the expression is that equation. Okay, so we've got the forces. The next step would be to work out the corresponding torques because of these particular forces. So we use the general expression, torque is force times distance. We've accounted for the sign notation for positive forces and negative forces on the right hand side and on the left hand side, which is the other way around. We defined it to make it positive in that way. Therefore, the torque because of the spring would then be the force because of the spring times the distance of the spring. Likewise, the torque because of the damper is the damping force times the distance of the damper. We're using these expressions. So substituting our result, that means the torque because of the damper is this expression. The distance between where the spring force is exerted and the pivot in this case would be L1. Then the torque of the damper would then be this expression times the pivot now for the damper, the distance between where the force of the damper, which is a retarding force, and the pivot. In this case, it would be L2, so we'd multiply it by L2. We substitute, and then we have this expression. We apply Newton's second law. Recall that the resultant force is just the vector sum of all the forces, and the resultant torque is just the vector sum of all the torques. Now, because of our choice of sign convention, we've accounted for the correct algebraic terms of the forces. So we then just say the resultant torque is equal to the torque because of the spring plus the torque because of the damper, and then this would be equal to this expression Okay. Now apply the rotational form of Newton's second law. This is Newton's second law for the forces and displacements in the x direction, Newton's second law for the forces and deflections in the y direction, Newton's second law for the rotations and torques in the theta direction. Alright, so this would then just imply that the resultant torque, which is this expression, all of this stuff is equal to the moment of inertia times the angular acceleration, which is equal to the moment of inertia times the double derivative of the rotation of the rod. What is the moment of inertia I? Well, moment of inertia is mass times distance squared. So we've got a rod. In general, we have the distance L1 to the pivot, a distance L2 to the endpoint, a total length of L3, but we don't know where the center of gravity is. We don't necessarily assume the pivot is in the middle of it. We could assume there's a center of gravity at a certain point, and then there would be a distance d between the pivot, the place where it is rotating, and the center of gravity. In this case, we would have to work out the moment of inertia using the parallel axis theorem. Now, if you recall, for a rod, they have the following expressions. The moment of inertia about the center of gravity is 1/12 the mass of the rod squared, and the moment of inertia about the endpoint is 1/3 mass length squared, if I recall correctly. Okay, so we know the moment of inertia through the center of gravity would be I is equal to 1/12 ml3 squared, because the total length is L3. And then using the parallel axis theorem, the moment of inertia between the center of gravity and the point where it's pivoting is the moment of inertia through the center of gravity plus the mass times the distance squared. So that means the moment of inertia about the point O is 1/12 mass length squared, the one through the center of gravity, plus the mass times this distance squared, which would be equal to the mass into 1/12 L squared plus d squared. So that's the moment of inertia through the point where it is pivoting. We can put this in, and then our equation of motion would then be as follows. Let's get this right. Mass we have this expression. We can put it on the other side to make it a homogeneous equation, and we would just write this down as follows. Like so. And that is our equation of motion. We can write our equation of motion in the standard form as follows. So just recall our equation of motion, just repeat it. It is 112 ml squared plus md squared theta dot dot plus c2l2 squared theta dot plus kl1 squared theta is equal to 0. That's our equation of motion. That is in the equivalent form m equivalent theta dot dot plus c equivalent theta dot plus k equivalent theta is equal to 0, where the equivalent mass is the terms in the curly brackets and that's our expression. And then we can put that equation into the standard form to give us the corresponding expressions. Okay, so that's how we develop the equation. So we would have a general expression for a rod, some springs, some dampers, various distances. We would then use this system to assume a variable that is independent. In this case it would be theta. We would work out the deflection of the spring and the damper, the velocity of the damper. We would take these expressions for the displacements and the velocities to work out the corresponding forces, as so. We would then have to think very, very carefully about an appropriate sign notation for positive forces on the one side, positive forces on the other side. In this particular case, because there's a pivot, the forces would be swapped around in order to be consistent for positive torques to be in an anti-clockwise direction. Don't mix it up. If you assume the positive forces are upwards on both sides, you'll get the wrong equation because it won't account for the sign convention. Using the forces, we worked out the corresponding torques. We applied vector superposition to work out the resultant torque, and then we applied Newton's laws to work out the equation of motion. Then, once we had the equation of motion, as so, we substituted all the terms, and then we were able to work out the equivalent mass. Basically, the equivalent mass is whatever's in front of the double derivative. The equivalent damping constant is whatever's in front of a first derivative, and the equivalent spring is whatever's in front of the other term, and all of that is equal to 0. In more advanced vibration analysis in the BTEC, you would have a non-zero term, basically an applied force. In this case, we are only looking at free vibrations. Free vibrations, so we have this system in terms of the angular deflections, but this system over here, this is our standard equation, can also be written in the form like so. These follow exactly the same mathematical form. So whether it is in terms of deflections or angles, as long as you end up with an equation, some constant times a double derivative in time plus some other constant times a first derivative in time plus some other constant times that is equal to 0, all of this stuff when you put in the numerical values, will give you the natural angular frequency and the damping factor. And depending on whether the damping factor is less than 1, this will be underdamped. If zeta is equal to 1, it would be critically damped, and if zeta is greater than 1, it would be overdamped. So depending on the magnitude of zeta, that would then give you the particular form of the equation. In this case it would be x of t, and in the particular system it would give you a solution for the angle as a function of time. So typically it would either be in a horizontal position at 0 time, and depending on the spring and the damper, the values of the masses and so on and so forth, it would give you an equation to work out how the rod rotates with time. In this case, that will give you the solution. If it was just a simple mass spring damper like so, if it's just a mass and a spring and a damper, it will give you a solution for x of t. If it is a rod at an angle, it would give you the solution for theta as a function of time. Although they look different equations, at the end of the day they have exactly the same mathematical form. So what happens is, in these types of problems, you have some physical problem, some geometry, some lengths, angles, whatever the case is. You define or you determine what is a free variable, what can be independently varied, and then everything else follows. In this case, we could have also theoretically worked out the deflections in terms of the vertical displacements, in which case we would then relate the deflections y in terms of theta using our underlying equation for the angle. It would be a bit more complicated. Over here we identified angle theta is independent of that. But in principle, we would just as well be able to derive an equation for we could just as well do that. We defined it in terms of theta, the angle. We could have just as easily defined it in terms of the vertical deflection yb going up and down. In this case, it's unnecessary because you can relate y to the angle by using the equation that equation. So if we solve this equation for the result in terms of theta, we would basically just multiply it by the length and would be able to work out the vertical deflection. What that means is, if we solve the equation in terms of theta in a computer program, we would actually be able to plot how the rod varies with time using Newton's equations of motion. In this case, there was only 1 degree of freedom. The entire motion can be defined in terms of one variable. In this case, it was theta. We could have just as well defined it in terms of this vertical deflection. Let's call it delta. There's nothing wrong with that. You would make your life a bit more complicated, but if you have a rotation, find out where it is rotating about and define the equation in terms of the rotation about that point. Alright, that is the end of the video, and we'll leave it over there. Thank you very much.